All right, let's start. Welcome to lecture 13 of Rob 101. This is the last lecture on chapter 9, vector spaces, part 2. So today we are going to talk about QR factorization. We are going to learn a new way to factorize matrices. And then we're going to learn a new way to solve the linear system of equations using this new factorization. And we're going to talk about how it comes out of the Gram-Schmidt process that we saw last time. And you will be hopefully pleased to see how much maybe more intuitive now you can see it is to use that Gram-Schmidt to solve linear system of equations. And then finally, we're going to talk about something that you had questions about it for a while. What is going to happen if I have less equations than unknowns? I have more variables than the number of equations. What will happen? So we never talked about that until today. Today, we're going to show you a way to solve that, and that's called the minimum norm solution to the system of linear equations that is underdetermined. So we're going to cover a lot of new topics today, and we will build on your knowledge that we covered so far.
Hey, Monty, can you share your screen?
Oh, sorry. Screen is not shared on Zoom.
Hey. Another life is hard issue in Rob 101.
Everybody's quiet. Complain when something is not working. All right, so a recap from last time. Last time we talked about a process that's called Gram-Schmidt process. And what it would do, it would take a set of vectors that are linearly independent, and I would turn them into a set of vectors that are orthogonal. And then we would normalize them, and we would get a set of orthonormal vectors. And then we talked about the geometry, and then the general process was that take the first vector and then subtract the overlapping part from the second vector, and then for the third vector, subtract the overlapping part from the first and the second one, and so on. So with step K, we would take the kth vector and then subtract all the previous overlapping parts from that vector. So as a result of this process that is using the dot product we learned last time, we would get a set of new vectors, v1, v2, and vm. These vectors are orthogonal. That means if you send them through the Gram-Schmidt process, take the dot product of every two of them, then it will be 0. They are orthogonal. We removed the overlapping part. Gram-Schmidt process preserves the span of the set of vectors. It will not change the span. That means the set of the new vectors still includes all the linear combinations of the original set of vectors. So that's good. It will not change the span, because if we would change it later, if we want to solve linear system, that would be a problem, right? Because that would change the set of solution, because we were talking about B should be in the column of span, and then if the span is changed, that means something is different. We're not dealing with the same system of equations. So it was important to note that the Gram-Schmidt process preserves the span, and the new set of vectors are also linearly independent. And finally, we could normalize them. For every new vector, divide them by the norm, and they're orthogonal and they're normalized. Now we have a set of orthonormal vectors. Every two of them, every pair of vectors in this set, they're orthogonal and normalized. So this is what we covered last week in the previous lecture. Today we're going to relate this to a new factorization called QR factorization. Now, and the way we're going to do that, instead of an arbitrary set of vectors, now we're going to talk about a matrix and columns of that matrix. So imagine we have a matrix A, n by m. Its columns are linearly independent. Now, it is a fact that we can prove that if, for this matrix A, there exists an orthogonal matrix Q, n by m, its columns are orthogonal, and an upper triangular matrix m by m called R, and you can factorize any such matrix to QR. So A, n by m, Q orthogonal n by m, the columns of Q are orthogonal. R upper triangular, remember upper triangular, 0, all the elements below diagonal. M by M. So this is true. Now we're going to find out how to get this Q and R. So if you have A, n by m, columns are linearly independent, you can always have QR. This is called QR factorization or decomposition also, just like LU. Both are, they mean the same thing. Now we're going to learn how to construct Q and R based on what we have learned so far. Suppose the set of vectors u1 to um, they are columns of A. Now if they're columns of A, the order is of course important. We have u1, u2, um. This is our n by m matrix. So the set of vectors is actually the columns of A. We use the columns of A, we apply the Gram-Schmidt process to the columns of A, and that will give you a set of vectors v1 to vm. These vectors are orthogonal. Then we normalize them, and then we stack them in a row to form another m by n by m matrix. And then we call this matrix Q. So Q is actually coming directly out of the Gram-Schmidt process. When you apply that to the columns of a matrix, you get Q. Now, once you implement your Gram-Schmidt process or modified version of that, which has the normalization before actually doing calculation, it gives a better result numerically. Then you have your functions, you pass your matrix, you get Q. You can get your orthonormal matrix Q by passing your matrix to that modified Gram-Schmidt function. So that's how we construct Q. it is clear that columns of Q are orthogonal, right? And normalized, orthonormal. That's just the side of that's just the product of the Gram-Schmidt process. We just defined Q to be this way. Now, if I can convert Q to, so Q is orthonormal, so if you calculate Q transpose Q, you get the identity matrix of size M. So if I have Q, and I know R, I know A, it shouldn't be too hard so I know A, I want A to be QR. I just calculated Q. I know exactly what Q is. Applying Gram-Schmidt process to the columns of A. Let's multiply both sides from left by Q transpose. Now I know that Q transpose Q is just the identity matrix. M by M, R is M by M. So this is actually just R. So then I learned that R is Q transpose A. So actually we have R as soon as we create Q. So as soon as you apply Gram-Schmidt process to the columns of A, you get Q, you know A, so R will be Q transpose A. And that's your factorization. Now, of course, you don't have to think about all these matrix multiplication that is going on. We're going to see soon something that is more explainable. This is a little too black box, maybe. You don't really see the structure of R here, because we said R is upper triangular. You have no reason to believe here R is upper triangular yet, but it is. And we will see soon. So the fact that R is Q transpose A, it's just by knowing that A, by construction, we want it to be QR, and then we can get Q, and then we get R. Now, let's relate it to what we had before, because we said if the columns of A are linearly independent, right? If and only if the system of linear equations A x equals 0 has a unique solution, right? And a condition for that was, if it's a square, determinant shouldn't be 0. If it's rectangular, right, tall matrix A transpose A, determinants of A transpose A shouldn't be 0. And we talked about that. What about QR? Now we know that the columns are independent. That means that AX equals 0 has a unique solution. And we know that A basically is QR. We substitute A to be QR, and then we multiply from left by Q. Q transpose Q is, of course, the identity again. So we're left with Rx equals 0. Now, R is a square M by M matrix, so we can talk about the determinant of R. If the determinant of R is not 0, that should imply that we have a unique solution, because that means the columns of A are linearly independent, okay? So with QR, we also have an easy way to check whether there is a unique solution or not. You can look at the determinant of R, and then we will see soon that R is upper triangular. The determinant of triangular matrix is, of course, the product of its diagonal entries. So that means it doesn't have any zeros on the diagonal. So let's see an example before we talked about the triangular structure. Suppose we have a matrix, 3 by 3. We want to calculate the QR factorization of this matrix. What should we do? Yes, let's do Gram-Schmidt. Or should we check if the columns of A are linearly independent first? Because that was an assumption before applying Gram-Schmidt. Now you can try it, but at some point it's going to be a problem if they're not linearly independent. You get so the determinant of R won't be non-zero. So let's take the columns of A. So by the way, if in general you could check the determinant of A transpose A, right? If you want to know if the columns of A are linearly independent or not. But here A is square. You can just take the determinant of A. So the columns of A will give us this set of 3 vectors. I'm going to skip the Gram-Schmidt process because that's
so just to clarify, if the determinant of R is 0, does that mean that the columns of A are linearly independent? Or there is a...
Yeah, there's a problem to begin with. We might not be at that step to begin with, right? Because we go through Gram-Schmidt with linearly independent set of vectors, which we talked about LU. It was more general. It could just do any, we could apply it to any matrix, even LD, LT. If you remember, we could apply it to A transpose A, or A if it's square, even if the determinant is 0. Then it would show us which columns are linearly independent. We talked about it, right? In details. But here we assume the columns are linearly independent. Now we apply the Gram-Schmidt, we get these vectors, this set of orthonormal vectors. Then we stack them in columns of Q. So once you understand the Gram-Schmidt process, you can think about it as a function, right? You pass your set of vectors, and you get your set of orthonormal vectors. And maybe you code it once, and that should work for you. In Rob 101, and later you can, of course, use other libraries too. So let's stack them in Q in a row, and then create Q. Why approximately? Why this is not exactly Q?
Because we're dealing with the radicals, so it's not exact since it's technically infinite.
Right. You see that a lot of square root of 38 divided by 38, square root of 2. There's going to be rounding error here, right? It's not exact. And later you will see I'll cut more numbers to fit matrices in my slides. In books you have more floating point numbers. So these are not exact. This is not a perfect solution. It's up to a rounding error, machine precision, that's just the solution we get, right? Now you could write it equality, but in general you should be aware that this is an approximate because of rounding errors. So we know that R will be Q transpose A. Very interesting. It is upper triangular. Sounds like the legend is true. R is upper triangular. We've been moving forward with ancient wisdom. R is upper triangular, just prove it. This is not comforting, right? Because you don't want to every time calculate and check to make sure R is upper triangular. How can you give a recipe to solve linear systems if it's not? Because then back substitution won't be applicable. Again, approximation sign here because, again, rounding errors. If Q is approximated, then R, of course, will be approximated. Multiplying Q by A is only going to make it worse. But these are not a problem. This is not a problem in practice. You don't need to be worried about too much.
Are you able to go back like 2 slides to
Yeah.
where you found after the Gram-Schmidt process?
Here?
Yeah.
Okay.
The terms with like the squigglies on them, those are those the vectors? Because I thought that having like V1 over the norm of V1, isn't that like the E term?
Oh yeah, we could call them E, right? Yeah,
Is that really all we care about? Like,
I'm being annoying and changing the notation, right?
but don't those have to be orthonormal? So wouldn't there shouldn't the norms be equal to? I guess are those like the sum or the norm is equal to 1 for those? Because aren't they like unit vectors?
No, this is basically 1 over the norm, right?
Oh, that's the
Yeah. So you could, but so the question is, what do you mean by these numbers? And we had E1, E2, E3. So I've changed the notation. You could name it anything, right? So that, please don't let that confuse you. And you could think about this as just 1 over norm of V2. But the thing is, in your code, the norm will be just a number you store. And then once you have your vector from the Gram-Schmidt process, you just divide by that. Now, in the modified Gram-Schmidt, that's a little out of patience of the lecture to go through it, but it's really just a tiny modification that you normalize inside the algorithm before subtracting the overlaps, makes it much cleaner, and then you get your normalized vectors as the output directly, so you don't have to do it, right?
So do we really only care about like the normalized vectors, like the normal ones, rather than the orthogonal ones?
Yes, the question is, do we care about orthogonal ones or orthonormal? We do want the orthonormal because Q must satisfy this Q transpose Q equals the identity, because if it's just orthogonal, it's not going to be the identity, right? The orthonormality means that they are orthogonal, but if you take the dot product, because they're unit vectors, the magnitude of the dot product will be 1. So there's a question in chat. So if the vectors are dependent, right, the Gram-Schmidt will give you 0 vector at some point. It's going to be a problem. And question is, I'm not sure if this was already asked or will be explained, but what do we gain from using QR factorization? When would we use it over Lu factorization? We anticipated that you will ask this. We prepared for this all weekend to answer this question. Yes, because it's a natural question. It's a great question that why do we care about QR? We had Lu that was giving us everything, right? I think it will make sense once we go through the solution of linear systems. There are 2 reasons. Now, you might think it's simpler, and it is very natural once you have the Gram-Schmidt as a tool, Gram-Schmidt process. The QR seems to be a very natural way to solve linear systems. But also, numerically speaking, QR factorization is the most stable factorization method. So it should be your first method of choice to solve linear system of equations. But LDLT, sometimes you care about the speed, is faster. It can be more than up to twice or more than that, faster than QR. So it really depends. Sometimes people care about really real-time and fast calculations. They know QR is better, but they try to make an algorithm that's very fast, and they may choose LDLT. Besides, LDLT was giving us a lot of other things, linear independence tests and all of that.
So why is QR factorization more stable?
Numerically more stable. Numerically more stable. It's robust to these rounding errors. That's because the modified Gram-Schmidt process is very stable, and that gives you directly Q, and then you have R. Basically, you get Q and R out of that process directly, and the modified version doesn't have this division by norm. You first make the vector normalize, so it is a unit vector, and then you just take the dot product to subtract the overlap. Whereas here, when you do all the calculations, and then in the end you divide it by number, that can ruin everything, right? It's typically something to avoid, dividing by numbers that can potentially be very large or small, right? So to answer your question again, Emerald, this is the journey we are on for today. Hopefully, by the end of today, let's see if you get your answer. Triangular structure of R. R is upper triangular. Everything below its diagonal is 0. Let's see if we can get R just out of the Gram-Schmidt process, just like we got Q. Instead of doing R, Q transpose A, it is nice if we just have it by the end of the algorithm. We don't have to do extra matrix multiplication. Besides, we can see the structure explicitly. Now, you recall that the Gram-Schmidt process was doing something like, it's easier to go back all the way to here. Now, at every step here, you can say R11 times U1. we writing it correctly? Let me go back. I think U and V are swapped. That's why I got confused. So let's just stay here. But the point is that those dot products and division by norm you can just put them in coefficients. Call them coefficients. And me going back, I think, confused you. Let's finish this part, and then we can talk about it if you find this part confusing. So keep the vector and the division by norm, because that's your unit vector, right? In the right-hand side, for V1, V2, V3, whatever else you have, dot product, norm, squared, or whatever, that was inside that process, call it just some coefficient, R11, R12, R21. So when you are in row 3, we name it as 1, 3, 2, 3, 3, 3, and so on. Now, as usual, let's say we have A. We have 3 columns, U1, U2, and U3. Now, we know that U1 is R11 times the unit vector. U2 is the sum of 2 unit vectors. And U3 is the sum of 3 unit vectors. So at the step K, UK, the kth column, it is the sum of k unit vectors. Now, some of you might recognize that this is really just multiplying Q by R, in the sense that I can construct Q as usual. We already talked about it. Q, always put your normalized vectors as its columns, and you have Q. So we have Q. If you multiply it by a matrix like this R, it will give you this. You can try and multiply them. It's going to be, if you go the standard way, you go this row times the column, you only get R11 times V1 divided by its norm. For the second one, you get the first term divided by the first one, plus the second divided by the second, and the third one is 0. For the third one, you get all 3 of them, right? By the standard way of multiplying matrices, you can do that. It's correct. Now, a better way to think about it is, however, the second way of multiplying matrices. We know that when you multiply a matrix by a vector, like A times X, the solution is just weighted, linear combinations of columns of A weighted by that vector components, right? So Q times the first column of R is just the first one, right, times the first column plus the second entry times the second column. This is the second way of multiplying matrices, column times rows. So when you do it for 2 matrices, you have to multiply columns by every you need to consider every column of the second matrix. All right, so these zeros will basically cancel, and what do we get? Aren't these are vectors? These are columns of A, right? It's the same equation that we had in Gram-Schmidt. These are just columns of A. So it is true that you can just have Q the way we talked about it, and R will be upper triangular. Because the way the Gram-Schmidt works, grab the first one, the second one involves the first one and the second one. The third one involves the first one, second one, and third one. So you always have this triangular structure. As you move down to the last column, what happens every time you add a new vector. So it forms this triangle structure for the coefficients. And then when we put them in a matrix, we get R. So that's how we know, we can prove that R is triangular always, just because of this triangular structure of Gram-Schmidt process.
Which coefficients are we talking about?
Okay.
R, the little r's?
Yeah, so question that I tried to answer early on comes up. That's why I went back first. So what coefficient, the question is what coefficients are we talking about? What is specifically R11, right? For that, let me go back to the Gram-Schmidt process. See if, I think we are using a different notation here, right? Because the left-hand side is V, whereas, no, that's true, that's correct. Okay, so now I'm a little confused because I can't remember the other slide's notation, but let's say I want my first vector to be first column of Q, right? So this must be, of course, U divided by norm of U1. So that is my normalized vector. And I can, if I multiply it by norm and divide it by norm, right? As if I've done nothing. So I can just say that this is R11 U1 divided by norm of U. So R is whatever we need to do to keep that normalized vector, and then the rest of it, just call it R, right? So it doesn't really matter what it is. We can calculate all of them exactly. It ends up being whatever you see here, right? Multiply and divide by the norm to make sure you keep your normalized vector, and then call the rest of it R for that index that you're tracking. Now, it is a little cumbersome to track, obviously, but when you do the algorithm, it's in the loop and it's doing it. We just store it. So I hope this clears, and please do go through it one time. Let me know if you have questions later. But R is whatever you need to keep your unit vector there, and then call the rest of the terms you have a coefficient, because it's going to be a scalar, ultimately, after all the dot products and norm operations we have here. All right, let me clear this. Now, for the second one, we have already V, right? V is not normalized. You can divide it by normal V and times normal V. Right, so whatever you have here, this whole giant term times this will give you the coefficient. Whatever we did here, you can repeat it for U2. So it is just manipulation of some terms and coefficient. So Emerald asks, is R always upper triangular, or could it be a lower triangular? It is always upper triangular because of here. So Emerald is asking if R can end up being a lower triangular matrix. And the answer is because the way we do here, see, the way we are doing things, we have and then the way we arrange columns of Q, right? We have wait. What do we have? Because, okay, I see why your confusion. I took that for granted because R, I think I can see it the way you're seeing it, Emerald, now. Because R is Q transpose A, right? When I tell you this triangular, now you were thinking that, well, I do have zeros here. Y ends up being like that. Because we do have this transpose, so it will flip it. So it ends up being upper triangular. Okay? So there's a transpose operation here, and that's why, although the rows that we follow from Gram-Schmidt, you see, looks like a lower triangular structure. But ultimately, the way we know it's upper triangular is here by construction, because when we put the vectors U1, U2, and U3 as a result of the Gram-Schmidt process. Now this, if Q is the way we defined it, this only makes sense if R has this structure, right? This is just purely looking at this. Don't worry about lines of the Gram-Schmidt. If I'm going to construct Q to be this way, R must be in this way, because when this upper triangular form, because when I multiply Q by R, I get A back. Then that must be the answer. So that's how we know R is upper triangular. Again, because when we multiply Q in the second way by columns, we have R1, R2, R3, we get lines of the Gram-Schmidt process. So it was a little misleading. If you look at this line that I drew, you say, well, how about we put it in a lower triangular matrix? But when you write the matrix multiplication, it should be actually upper triangular, because that's what makes the equation consistent. A equals Q times R. All right, so a lot of unknowing coefficients here. We don't want to do it by hand, right? So it's easy to I think impossible not to make mistake. If you had to do it every time, we're not going to do it like this. Just like you use LU to solve problems, right? You do your factorization and then you solve problems by computer. But it is important to know why R is upper triangular, because that's how we're going to define the solution. So first, suppose we are talking about solution of linear equations. Now, I'm talking about solution, right? So this is a square system, same number of variables, same number of equations. Suppose I factorize A to be QR. And the columns of A are, of course, linearly independent, so I can do this. Then I have AX equals B. I can substitute A to be Q times R times X equals B. Then I can multiply both sides by Q. And Q transpose Q, again, is the identity. Then I will get this interesting equation. R times Q equals Q transpose B. And R is upper triangular. Sounds like we can solve the problem already. Right? We know we can use back substitution. And in fact, that's how we do it. So whenever you're dealing with a square system of equations, the determinant of A is not 0, and you want to solve AX equals B, now remember, there is a solution if B is a linear combination of column of A. We assume there is a solution. Determinant is not 0, so it must be unique. Then we factor A to QR. For convenience, let's call Q transpose B to be B bar. That's going to be another vector, right? A n by m, x m by 1, b n by 1. Q n by m, right? So Q transpose will be m by n, b is n by 1, sorry, m by n. Therefore, B bar is what? What is the dimension of B bar? no interest to help out. Q is n by m, but Q transpose will be m by n, multiplied by a vector that is n by 1. This must be correct, m by 1. So purely for the sake of convenience, let's call B bar to be Q transpose times B. Then solve Rx equals B bar via back substitution, and you will have your solution. So you don't need to do twice, right? In LU, we had, what do we have? Forward, backward? Now we only have backward. Does that make it faster? That's the question. It doesn't. This is actually slower. So it's not the back substitution that makes the problem slow. I mean, it looks nicer, but the factorization is the costly part. And if you really want to know why it's slower in a course or a book on numerical analysis and algorithms, you count number of flops. How many operations you're doing, how many operations your computer needs to do, right? If you count those operations, then you realize that you're actually doing twice as many calculations as LU. Why should we use QR? It will be numerically more stable. Now, there are cases that you are dealing with problems that are nearly singular, right? The determinant is, vectors are very close, right? There's a danger of this rounding ends up making it singular. Then QR will be your better friend. If you do Cholesky or LDLT, then you increase the chance of dealing with singularity, right? Now, in general, that might not be your concern, but if you're building algorithms that you care about robustness, right? If you want to sell that product, you want it to work always. But of course, you're facing the challenge, do I have computational resources to do that? Or do I want it to be robust and I'm going to spend more calculation on this part, right? As an engineer, it's the call that you need to make, but slower, more robust, faster, less robust. There's a trade-off here. Usually, it's very rare something is faster and better. So you don't get mad when people don't believe. If you come up with something that they say, it's faster, better, there are cases, but those are usually really important results, breakthrough, doing things very differently, right? We usually face trade-off. So LU was back substitution, forward substitution here. We are just doing back substitution, although the bulk of the cost is on the factorization part again. We're not digging into numerical analysis in this course. It's a little beyond the scope of our course, but as a fact, I told you to just have it in mind when you use it. Let's look at an example. Not real-life example. Now, we had real-life examples of that. In simultaneous localization and mapping, we had a data set, we were processing the backend, the solver of that mapping problem was using Cholesky factorization by default because it was faster. But we were getting singularity when we were solving a linear system. It would tell us that the system becomes singular. Then we tried QR and suddenly it started working because we were guessing. Now, it could be a more fundamental problem because now you're dealing with actually dependent variables, right? Columns and maybe not enough rows in your matrix and so on. But it did solve our problem. And the problem is you don't see it because it's just large. You're not going to be able to look at a giant matrix and then try to draw a conclusion, right? So at that point, you're just going to rely on your knowledge that I know QR is going to be more robust. If there's any chance, that's going to solve it better. All right, so we have a 3x3 system of linear equations. We have A and B. We want to solve it using QR. First thing we do, we factorize A to Q and R. And we get a bunch of numbers. We know that Q must be orthogonal. You can verify, right? You can check that Q transpose Q is the identity. Now, this is a square system. Probably the other way is correct, too. You can get Q transpose, Q times Q transpose in this particular case. We form B, B bar, Q transpose times B. That will be a 3 vector. Now we are dealing with a triangular system of equations, R times X equals B bar, which gives you the result. Now let's talk about least squares solution. Now, when we have more equations and unknowns, we know that there's no exact, a lot of time we talked about it, there's no exact solution. We settled for minimum error solution, that was least squares solution. So A is n by m, columns are linearly independent. A is, again, Q times R, we factorize A. We know the columns of A are linearly independent. Now, well, I'm not going to repeat everything from last, was it last lecture or lecture before that? We talked about the least squares problem and the fact that least squares problem, least squares solution to the linear system satisfies the normal equation. And the normal equation is A transpose times A, X equals A transpose B. That was the main result of the least squares problem. So if I start from the normal equations, for convenience, I calculate A transpose A here. I know A is QR, so A transpose will be R transpose Q transpose. So R transpose Q transpose times Q times R. This is identity. So A transpose A is actually R transpose R. So we get the result here. The right-hand side, again, will be just R transpose Q transpose B. Now, if columns of A are linearly independent, we know R will be invertible, so we can actually multiply both sides by the inverse of R transpose and drop this, right? Because R will be invertible if the columns of A are linearly independent. So what we're left with is actually what we saw for the exact solution of linear system, for a square system. somewhat surprising, but also not surprising, because, well, this is more general. When it's exact, it reduces to the exact form, and that's always nice. So it's exactly the same. So you don't actually care if you have more rows, more equations than unknowns or not, if it's rectangular or square. As long as the columns of A are linearly independent, you apply your QR factorization, and then you can solve the problem by back substitution. So the least squares solution is also the same thing as the previous case. I took normal equations for granted. If you don't remember this, please refer to the least squares lecture. That's the main result from that lecture. And the condition that the columns of A are linearly independent means that A transpose times A is invertible. Its determinant is non-zero. We talked about that. So the pipeline or the steps to solve the problem are the same. Factorize A, calculate B bar, solve the back substitution, and you will have the answer. So the orthonormality of Q comes very handy when we're manipulating terms using QR factorization. Now let's cover a final case. We never talked about this, but you had questions about it, and I tried to dodge your questions, just ignore it. So what happens when I don't have enough number of rows? What if my matrix is wide? This is n by m, but now n is smaller than m. So imagine I have 3 variables, 3 columns, and then I have 2 equations, right? One equation is missing. I don't have enough information to exactly solve the solution. It's going to be n by 1. So we're going to learn how to solve this. So if we have less rows than equations, right? We have fewer equations than unknowns, then we have the condition that A will have its columns to be linearly dependent, because we have missing equation, and then there are arbitrary choices, and that can generate basically infinite number of solutions. So the columns of A ends up being dependent because of this wide structure of the matrix. We have more columns than rows. We call these systems of equations underdetermined. So the previous case that we have more rows than columns, that's called overdetermined. That's always good. That's usually the least squares problem. You assume you have more rows, more equations, and then you use least squares to solve it. This is trickier because now the problem is called underdetermined, and the columns of A are dependent. Because the minimum condition to solve for X is that we have the same number of equations as our unknown. That's the minimum we need. Should we give up? what can we do? One solution is to give up. When you wouldn't be able to control your car. In project 3, you will see that what we talked about, this is the case when you control a mobile robot, for example, or a Segway. It's called model predictive control. You want to solve for your control inputs, and then the problem is that you don't have enough equations, but you have a lot of variables to predict ahead in time. So it has very important applications. We do not give up. We want to find a way to solve it. Now, one question that might come up is that, is there a difference between being underdetermined and having an infinite number of solutions? And I'd like to remind you that there is a difference, because we talked about this, that B must be in the column space of A, no matter what. So if B is not in the column space of A, there is no solution, even if the system is underdetermined, right? So if B is in the column span of A, then we have infinite number of solutions, if the system is underdetermined. But if it's not in the column span, then there's no solution, as we had for previous cases. So, but we do have this condition that if rows of A are linearly independent, not columns, rows, for an underdetermined systems, we have infinite number of solutions. Next chapter might shine some light on this when we talk about rank of a matrix. This really means that if somebody's finished linear algebra and then we are free to use all the terms, we say that A is full rank. But we don't know what is rank. We never talked about it. So for now, we're going to talk about rows of A must be linearly independent, then you have infinite number of solutions. More on this in chapter 10. Now, a minimum norm solution is what we're going to settle with. We need to do something. A very standard practice is to go for minimum norm solutions. Find the solution with the smallest magnitude. Now, in terms of, for example, cost could be minimum cost, right? In terms of weight could be minimum weight. In terms of energy, minimum energy. So physically it makes sense, right, to minimize some quantity that you'd like to minimize, consumption. So the minimum norm solution is saying that find the solution that minimizes the norm of x such that also satisfies the equation ax equals b, even though I have less rows, make sure it satisfies that equation. So there are, again, infinite number of solutions. Find the one that satisfies the equation and has minimum norm. Now, it turns out the solution to that is this. Why? Two ways, again, to show it. You can check the book for that, or if you have a knowledge of calculus, it actually is an easy solution for that. I won't talk about it now. Do let me know on Piazza or office hours. There's a page note in the book to verify why this is a solution. But regardless, that's the solution of the minimum norm problem. Do you notice any difference with the least squares solution? Previously, we had A transpose A, right? Now we have A transpose. So it's like a mirrored version of that. Previously, we had A transpose A inverse times A transpose B. Now we have A transpose times A transpose inverse. So this is not the same problem, right? But you might see some similarities and differences. So the solution is A transpose. Now A is a wide matrix, so A transpose will be a tall matrix. And A times A transpose will be a square matrix. That's why if the rows of A are linearly independent, then A transpose, A times A transpose will be invertible. That's why we need that. Now you can call this alpha. So A times A transpose alpha equals B. Now you could, if for small problems, you could invert A transpose, but if the problem is large, you shouldn't invert it. We should solve this system of linear equations. This is a square system of linear equations, right? A transpose will be n by n. Now, that's a little painful. Let's see if we can make it simpler. How about we factorize A transpose instead of A? See what we get out of this. Because the columns of A transpose are the rows of A. So then the columns of A transpose are linearly independent, and then we can use Gram-Schmidt and factorize A transpose, right? So because of that, then we get A transpose to be QR, and A, of course, will be R transpose times Q transpose. And then you get A times A transpose to be R transpose Q transpose times QR, identity. So A times A transpose will be R transpose R. This is looks like a good thing, but we don't know yet. So let's see. We have A times A transpose inverse. You get Q, R, R, transpose R inverse. Now, you remember A, B inverse is B inverse, A inverse. So this is actually going to be Q, R, R inverse, R transpose. And that's Q identity, Q, R transpose. So there's an inverse here. And A transpose inverse, you can write it like this. That means transpose N inverse. So I can write this Q, R transpose inverse. So we managed to get rid of a lot of terms using QR factorization. So we are left with Q times R transpose inverse times B. How about we call this in this time, because it's different from last time, we give it a different name. This is beta. Then the solution is Q times beta, and beta is, because R is invertible, is R transpose times beta equals B. This is Now, R is upper triangular. R transpose is lower triangular. We do a forward substitution. We find beta, and then we solve for the minimum norm solution. So QR actually makes it very easy to solve the minimum norm solution. So R transpose is lower triangular. It's the transpose of an upper triangular matrix. We solve R transpose beta equals B using forward substitution. To solve a system of underdetermined equations, first check and make sure the columns of A are linearly independent. This is the same thing as saying the rows of A. So columns of A transpose are linearly independent. This is the same thing as saying rows of A are linearly independent. Then calculate the factorization of QR factorization of A transpose instead of A. Then solve for beta using R transpose beta equals B using forward substitution, and then your solution will be Q times beta. So the same QR factorization solved this problem too, not any harder. If you have forward and back substitution in your toolbox and you have QR factorization, and you have a way of checking linear independence of columns and rows, then you can solve both determined, overdetermined, and underdetermined system of equations. Let's look at an example. I have 3 variables and 2 equations. We want to solve this. First, we check that the columns of A transpose to be linearly independent. Looks like they are. Then we factorize A transpose, we get Q and R. Now, your algorithm doesn't care if you pass A or A transpose, right? A transpose is just another matrix for your algorithm, as long as the columns are linearly independent. So nothing has changed in your program. So A transpose is QR. Let's do the forward substitution to find beta. We get it. And then your minimum norm solution will be Q times beta. And that's the solution here. Now, there are infinite number of solutions. This is the one that has the minimum norm. So the set of solutions is actually much bigger because every vector in the null space of your matrix A, you can add it to this and it's a solution still, right? And in fact, you can choose, if it's a physical problem, you can play with the vectors that are in null space to change the solution if you must design according to some criteria. It's up to you. But we don't do it here. I wanted to give you extra information, then I thought you might get confused. I'm going to give it to you anyway. That solution, minimum norm solution, is actually geometrically orthogonal to the null space of matrix A. Maybe it doesn't make sense, but as you learn more and think about these things more, it is true that this minimum norm solution, it is orthogonal to the null space of your matrix A. I think there's a note in the book using Pythagorean theorem, and it implies that, if you look into it. There's an implication there that that's the case. Although it might not be explicitly pointing out this property. Now, why should we believe this is a solution? Well, we know it is, based on math. Let's verify it numerically. Ax minus b was a constraint. When you say arg min, you may minimize the norm of x and respect this constraint, right? It's only a solution of this problem if it's the minimum and also satisfies this equation. So we check if it satisfies the constraint, ax minus b, and it does. This is practically 0. It's a pretty good solution. Now, if you ever take a course, I think there will be a course in robotics for optimization, but maybe other departments have it too. If you take a course in optimization, this will be an instance of a constraint optimization. You want to optimize an objective, you have constraints, makes it harder. One very interesting method is called the method of Lagrange multipliers. And that's the combination of that with calculus is a very handy way to prove these results. But it is out of context of Rob 101. I highly recommend taking a course in optimization if you're interested in these problems. And in control engineering, constraint optimizations are the standard tools for problem solving. So that's it for today and chapter 9. We finished chapter 9. It was probably the heaviest chapter maybe so far. The content was a little more challenging. Chapter 10 is actually the last chapter. We're going to have 2 lectures on it. It's the last chapter on official linear algebra. We're going to add more topics.